Greetings to you. We are going to discuss third module, that is interaction of electromagnetic radiation with matter. Earlier we had in the module 1 we had an introduction, and then in module 2 we studied about the atomic structure. Now as you know, most of these spectroscopic techniques use electromagnetic radiation, and the electromagnetic radiation is a very important concept because it interacts with the matter to give you a variety of wavelengths. Okay. So, we are continuing with our this thing. So, basically what we want to discuss today is about the nature of electromagnetic radiation. So, what is electromagnetic radiation? It is the energy travelling through space unaccompanied by the matter. That means, there will be radiations, but not with the matter. The radiation usually traverses as waves or as small bundles of energy called as photons. In classical physics, electromagnetic radiation is basically a force field in space with characteristic frequency, velocity and intensity. It is characterized by an electric field and a magnetic field, that is both of them are vectors. Okay. So, both these vectors are associated with all electromagnetic radiation, and they are oriented perpendicular to each other and to the direction of propagation. So, on passing through the matter, the radiation may interact with the particles having electric charge or magnetic moment, resulting in a transfer of energy to the other. Now, if I tell you so much about the theory, probably you may get confused a little bit, but this is what we mean. It is electromagnetic radiation is a force field, it is energy moving in one direction, there is an electric field marked with red, and there is a magnetic field marked with blue, and this is known as wavelength. So, all electromagnetic radiation are characterized by two components, one is electric field and another is magnetic field. Okay. So, all electromagnetic radiations are therefore characterized by wavelength denoted by lambda or frequency. So, what do we mean by wavelength? It is defined as the distance between successive maxima or minima. The frequency is the number of cycles occurring per second. The wavelength and frequency are related by lambda is equal to v by mu, where v is the velocity of the propagation, and all electromagnetic radiations have the same velocity through vacuum. That is, the number is known, 2.9979 into 10 raised to 10 centimeters per second. You can take it for granted that it is approximately 3 into 10 raised to 10 for easy remembrance, 3 into 10 raised to 10. So, most of the electromagnetic radiation traverses, and it goes like this, and this is the wavelength between two crests, and this also can be wavelength. So, this is what we should understand. We can do a little bit more numbers. For example, lambda is nothing but velocity of light divided by frequency. So, that is 2.9979 into 10 raised to 10. Frequency is expressed as the number of cycles per second or as wave numbers. So, wave number is denoted by mu bar, and that is given by mu bar is equal to 1 over lambda. That is, units would be in centimeters inverse, the distribution of spectral intensity in the black body radiation was best explained by Max Planck in 1900 by uniting the corpuscular theory and wave theory as a relation between the energy of a quantum of radiation to the frequency given by delta E is equal to h mu or h c by lambda. Okay. So, in this equation delta E is the energy of quantum of radiation and mu is the frequency of radiation. H is known as Planck's constant, that is 6.624 into 10 raised to minus 27 ergs second. The interaction of matter with radiation thus involves exact quantized energy of the substance. So, there is no continued energy transfer in that. So, every elementary system, whether nucleus, atom or a molecule, thus has a number of quantized energy states, and absorption or emission of energy takes place only if the energy of the matter is equivalent to the difference between the energy states. So, otherwise the radiation is transmitted without any change through the matter. So, this is a very important concept. That means, if you want to effect change in the matter, you have to supply exact amount of energy characterized by the matter. So, the energy or frequency which the incoming photon is absorbed is given by the Bohr equation, that is h mu is equal to h c by lambda, that is expressed as energy of the final state and energy of the initial state of the substance. So, in the case of emission, the energy of the radiation is given by h mu is equal to h c by lambda, that is E I minus E f. So, here we are talking about the absorption. Here we are talking about equation 1.5 refers to absorption, 1.6 refers to emission. So, in actual practice, whenever a radiation of multiple frequency interacts with the matter, part of the energy may be used up in absorption, emission, reflection, refraction, diffraction or in scattering. So many possibilities are there whenever there is interaction of the electromagnetic radiation. So, I can put it in an equation something like this: energy is equal to the sum total of energy absorbed, energy emitted, energy reflected, energy refracted, energy diffracted, energy scattered and so many other phenomena. So, various types of quantized energy changes occurring in each region of the spectrum, and the magnitude of energies involved have been traditionally used for a variety of spectrochemical techniques. The energy ranges are generally classified as gamma rays, X-rays, UV visible rays, infrared, microwaves, radio frequency. I think most of you are familiar with this kind of radiations. They are all part of the electromagnetic radiation only. So, the absorption of radiation occurring at different wavelengths and the associated spectroscopic techniques I am giving in the table 1, and this is the absorption of the electromagnetic representation of the electromagnetic radiation. So, at one end of the spectrum we have gamma rays, then X-rays, ultraviolet, visible, infrared, microwave, and then FM, and then AM, that is radio waves, and then long radio waves are also present there, and the increasing the top portion I am showing you the increasing frequency. So, gamma rays are the shortest and having maximum number of frequency, and the wavelength also would be very less. So, almost 10 to the power of minus 16 angstroms, etc. And you can see that in gamma rays an analytical technique based on nuclear interactions can be used. These are such radiations are typically used in nuclear establishments for measurement of radiation and things like that. And X-rays are core level electrons, ultraviolet rays correspond to valence electrons, and then visible range also refers to valence electrons, infrared refers to molecular vibrations, microwave and molecular rotations, electron spin, electron radio waves, etc. So, with each radiation, an analytical technique is available which can be used as a spectroscopic basis. So, you can also see that the visible range is only a very small portion of the total electromagnetic radiation, isn't it? So, here we see from one end 400 to 700 nanometers. So, violet, ultraviolet, VIBGOR, that is rainbow colors you would be seeing all over the in visible range. Okay. Now, even among the visible range, what you see actually is a complementary hue rather than the transmitted color. Suppose I take ultraviolet, you do not see any color at all, but between 380 and 435 what is transmitted is violet, but complementary hue is what you see in the solution, that is yellowish green. Similarly, 435 to 480, that is blue transmitted color, and yellow is the complementary hue. Similarly, 480 490 greenish blue and orange, 490 to 500 that is red, and 500 to 560 if it absorbs you would see a purple color, and then 560 to 580 you will be seeing violet, 580 to 595 is blue color, and 590 to 625 is greenish blue, and beyond that is bluish green, and above 780 it is near infrared, that is red color only you will be seeing. So, it must be noted that there are no sharp differences in color at any wavelength. They all sort of merge themselves in reddish, blue green, green blue, greenish blue, like that. But they rather merge into one another in a diffused manner. There is no sharp differences that above 380 you will see only one color, above 390 you will see only one color, nothing like that. So, this process is a specific phenomena related to the characteristic molecular structure. Okay. So, you can imagine a rainbow where the colors, you will see all the colors, but there are no sharp differences in the color. Okay. So, for a given excitation process, what happens is a molecule absorbs a discrete quanta of energy resulting in an absorption line. However, since a group of molecules exist in a number of vibrational and rotational energy levels, each differing by a small amount of energy, a series of absorption lines appear over a small range and give rise to an absorption peak or a band. So, this is how the absorption takes place. For example, I take a substance, pass the electromagnetic radiation, it absorbs. So, you will see a complementary hue. Okay. but why they are so diffuse? Because the rotational and vibrational energy levels of the absorbing medium are not they are closely comparable in terms of energy. So, instead of getting a simple line spectra, you will get a small peak like this. Okay. So, this you should understand. So, if we look at monoatomic substances normally existing in gaseous state and that absorb radiation only through an increase in their electronic energy. These are quantized again and appears in various subshells. For example, here I am showing 1s, 2s, 2p, 3s, 3p, 4s, 3d, like that. There are different energy levels and the electrons will be moving from 1s to 2s, 2s to 2p, like that. There will be transition that give rise to an absorption peak. Okay. Now, for polyatomic molecules, that is, if a substance is having a number of atoms, unlike single atom like hydrogen, okay, the electronic transitions involve molecular orbitals requiring energy in the ultraviolet region. These are far more complex usually. They involve vibrational and rotational energy levels. Therefore, the total energy may be considered as sum of the contributions from all states of energy. Okay. So, for each electronic energy state of the molecule, there exist several possible vibrational states, and for each of these in terms of numerous rotational energy. So, that means for every electronic energy level, the energy is this much, but with each electronic energy level there will be number of small steps defined as vibrational energy level. Okay. So, for each vibrational energy level in turn, there will be a number of rotational energy levels. So, if you look at the structure of an atom, a polyatomic molecule, you would see that the energy levels are diffuse, not so sharp. So, but electronic transitions in organic molecules are characterized by promotion of electrons from bonding or non-bonding electron orbitals to excited state anti-bonding orbitals. I have not taught you about bonding and anti-bonding orbitals yet. So, but for you to remember, the bonding orbitals are something like, you can imagine a molecule like methane, okay, carbon, hydrogen, CH4, correct. So, sigma bond, it is most of you would have studied sigma bond, pi bond, etc. So, if I take the molecule, excite it, the energy of the excited molecule will be slightly higher, it becomes so much unstable. Okay. So, the what happens to the system? So, the electrons go to the next higher energy level, that is known as anti-bonding orbital. So, for each sigma bond, let us say, there will be an anti-bonding sigma star anti-bonding orbital. For pi orbitals, that is double bonds, there will be pi star. Okay. Then there are certain number of electrons having n non-bonding electrons. For example, in alcohol, the oxygen is having 2 pairs of electrons on oxygen, and they in turn can get excited to pi star. So, we get transition from sigma to sigma star, pi to pi star, n to pi star, and several other possibilities. So, we will not go much into details of this, but except that sigma orbitals and non-bonding orbitals are designated as sigma star, pi star, etc. Okay. In addition, many molecules contain electrons that are not directly involved in bonding. This I have already explained to you with respect to oxygen, but there are many other elements like sulfur, nitrogen, halogens, etc. They also have a number of non-bonding electrons, and the possibility of transition is always there. So, in the excited state, some if not all the electrons occupy antibonding orbitals. Most of the excitation, if not all the electrons, majority of them will occupy antibonding orbitals. So, the molecule even in the antibonding orbital, even if the molecule electron is excited, the molecule retains sufficient bonding character to ensure the stability of the molecule. Otherwise, dissociation will occur. So, the dissociation we do not want, we just want it to go to next higher energy level and stay there. So, the electronic transitions possible in ultraviolet and visible spectrum are sigma to sigma star, sigma to pi star, and pi to pi star, n to pi star, etc. The energy required for these transitions decreases in the same order as shown below, that is sigma to sigma star, sigma to pi star, and pi to pi star. So, the saturated hydrocarbons have only sigma bonds. Okay. So, the energy required would be very high to excite the electrons. Alcohols, chlorides, etc., they have non-bonding electrons. Saturated aldehydes and ketones, they also have non-bonding electrons present on the oxygen atoms. Okay. So, the electronic excited energy levels, how much energy is required to supply? That is a moot point. In general, we feel that the energy ranges from 35.71 kilocalories in the visible range to regions several hundred kilocalories in the far ultraviolet. So, each electronic level associated with several vibrational modes and maximum population is at the vibrational level 0. So, consequently, the absorption arising out of this transition will be most intense, because maximum number of electrons are there in the ground state, that is vibrational energy level 0. So, a broad absorption band results. So, sigma to sigma star transitions are very energetic and are found only below 200 nanometers, that is in the vacuum ultraviolet range. Okay. So, spectroscopy is the measurement and interpretation of the electromagnetic radiation resulting in the absorption, emission, reflection, etc. This we have already covered. So, all these processes are associated with energy changes, and the electromagnetic radiation may be considered as a wave which carries energy, and this we have seen, as the name suggests, electromagnetic radiation, electromagnetic. So, it has an electric field and magnetic field. So, this is what we had already shown you earlier. So, this is polarized radiation. So, many properties of the electromagnetic radiation are described by considering it as a classical sinusoidal wave, that is like a sine wave with characteristic wavelength, frequency, velocity and amplitude. So, electromagnetic radiation passes through vacuum unlike sound waves. So, sound waves do not travel in vacuum, whereas electromagnetic radiations travel through the vacuum. However, some of the electromagnetic radiations are both described best as a number of streaming particles, that is, you take an electromagnetic radiation, you can imagine the number of photons coming out from a given source. So, the photons may be considered as particles of or bundles of energy. So, they are best described as a number of streaming particles, and according to Heisenberg's principle, it is impossible to measure the wave and particle properties of a photon simultaneously. This is a very important concept with respect to spectroscopy. Therefore, it is convenient to imagine as photons as particles having specific amount of energy radiating from a source and characterized by an electromagnetic wave. So, the wavelength of radiation lambda can be visualized as the distance between two maxima of either electrical or magnetic component. The frequency, as we have already said, it is the number of waves in electromagnetic radiation passing through any fixed point p per unit time. So, when a photon passes a particular region of space, the electric and magnetic field oscillate with the frequency. Therefore, only frequency is truly characteristic of a particular radiation. This you should understand. So, you want to describe the electromagnetic radiation, whatever you wish to say, if you say the frequency, it is well defined for the electromagnetic radiation. So, how do we say mathematically? Then we have to say it is a sine wave. So, mathematically A is equal to A0 into sin theta. So, A is the amplitude at any point, A0 is the peak amplitude and theta is the continuous variable. So, these are all basically physics you would have studied in high school in second year PU or something like that. Okay. So, I am only giving you some sort of an insight into these things. I am making a passing remark just to refresh your memory. Okay. So, alternately we can say A is equal to A0 into sin omega t. So, where omega t is nothing but theta and omega is the angular velocity in radians per unit time. So, a complete cycle occurs when omega t changes from 0 to 360, that is understandable. So, after it keeps on moving, so when it starts moving, after every 360 degrees it comes back to 0 level, again 360 it will move again 0 level it will come. So, 0 to 360 degrees is where the repetition of the electromagnetic radiation occurs. So, the time over which one completely occurs repetition is given by T cycle, that is omega by 2 pi, or frequency what we do define now is 1 over T cycles or 2 pi by omega. Okay. So, for any wave moving at a constant velocity v, we can write v is equal to v into lambda, where v is the frequency in milliseconds inverse, v is in hertz, that is cycles per second, and lambda is in meters. We can say meters, nanometers, whatever are the appropriate units. So, the frequency is proportional to the energy E of the photon as given by E is equal to h mu. So, sometimes it is convenient to use wave number. This also we have covered earlier, and that is the wave number refers more to infrared radiation. We will study that sometime in the next course with time permits. So, in general, what I want to do now is I want to give you units of electromagnetic radiation For example, take a look at this. The nanometer is a unit for wavelength and it is used in UV visible near infrared spectroscopy. Angstroms is X-ray and UV visible. In older work they used to use UV visible, nowadays we call it nanometers, that is fair enough. And millimicrons, again it is in the visible range, again not so popular nowadays. And microns and micrometer used in infrared, wave number again infrared and UV visible, it is less common in UV visible. Similarly, electron volt, that is for X-ray and gamma rays, because they have very high energy, it is better to define them by electron volts. So, hertz, radio frequency and microwave, cycles per second CPS is meant for radio frequency. So, these are the different kinds of units used in different spectroscopic techniques. So, the interconnection of this is all these wavelengths can be converted into one another, and this table describes the interconversion of one unit to another of all electromagnetic radiations. Okay. You can study this and try to remember. It may be noted that regardless of the units of expression, any electromagnetic radiation or frequency will have unique wavelength and energy. So, the longer the wavelength, lower is the energy and frequency. Energy is closely related to the temperature of any object. It can be expressed as E is proportional to kB into T, where kB is the Boltzmann constant, that corresponds to 1.380 into 10 raised to minus 16 ergs per K per degree per atom, or 1.380 into 10 raised to minus 23 joules per degree per atmosphere. So, if we consider the energy per molecule of the material, E is proportional to RT, that is R is the gas constant given by this number 8.3145 into 10 raised to 7, and you can also write the same thing in joules. Okay. So, the energy of the photon should not be confused with the brightness. So, this is a very important concept again. Brightness or intensity of the source has nothing to do with the energy of the photons, but it relates to the color of the light, that is for sure. So, the power of a light source is given by P is equal to number of photons multiplied by the photonic energy. It is the energy of a beam of radiation that reaches a given area per second. So, if I give you a small light source like a torch, the energy that falls when I project it on the screen, it reaches a given area per second. So, intensity of the source of radiation is the power emanating per unit solid angle. Okay. So, these are all basically physics concepts. You can refresh your memory later. So, this is the electromagnetic radiation. We have already seen another type of presentation in terms of frequency, wavelength, etc. And as you can see here, the color visible portion is only a small portion of this. So, remaining are all UV, visible, IR, microwave, radio, waves, etc. So, now we will discuss about the transmission of radiation. Okay. So, the rate of propagation of electromagnetic radiation. We will spend the next half an hour studying that.